In this video, I'm going to continue to talk about the functions sine and cosine. In particular, I'm going to look at the answers that we get when we evaluate the functions for angles ranging from 0 to 360 degrees. We're going to see that the answers are not unique. There's going to be a lot of repetition in the types of answers that we get. And this in turn will introduce an idea called reference angles and how those reference angles can minimize your responsibilities. We're going to begin with two angle measurements, 40 degrees and 140 degrees. And we're going to evaluate the sine function and the cosine function using those two angle measurements. But before we do that, before we go to the calculator and type these in, what I want to do is create a diagram that shows these two angles. So we're going to start with a circle that's centered at the origin, which I already have a picture of here. And we're going to graph the 40 degrees. That would be an acute angle that'll be over here. And we're also going to be graphing 140 degrees, which is an obtuse angle. So that's going to be in quadrant 2. In addition to graphing those angles, what we're going to go ahead and do is add in the components. That would be the x component and the y component. All right, so let's go ahead and take a protractor and line that up at the center. And 40 degrees is going to be in quadrant 1. All right, so you're going to notice that the 40 degrees is right there. That's if you're counting up, so you get 0, 10, 20, 30, and 40. Okay, and I'm going to go ahead and mark that there. Let's go ahead and connect that to the origin. I don't need to draw all the way out, so I'm just going to go from the edge of the circle out like that. Okay, and that is 40 degrees. In addition to that, what I want here are the components. I want to be able to see the x component that we have here and also the y component. And we might as well just go ahead and add an r for the radius. All right, so for 140 degrees, that would also be on the inside set of numbers. We're going to be counting up here, so we're going to count 0, 10, 20, 30, so on. Once you get to 140, there we are. Going to go ahead and line that up. All right. Now that one's a little bit of a, I can't label 140 there, so it's a little bit of a tricky one here. What I need to do is show that that is 140. Okay, because we're measuring all the way out from the initial ray out to that spot there. All right, and in addition, here's the y component, and here is the x component. Now, if we take a step back and we look at the picture here, you're going to start to realize something that's going to be important for how we evaluate the angles a little bit later on, which is that these two pictures appear to be reflections across the y-axis. They appear to be reflections across the y-axis. And it in fact is true because remember that from here all the way around to that side is 180 degrees. That's 180 degrees. And right here we have 140. So if we subtract 140 from 180, you actually get right here 40 degrees. So these actually are the same thing. They are mirror images of each other. Okay, except that there's one difference about the two of them. There's one difference about the two of them. If you look close at the components, okay, I didn't label all the components here, so I'll go ahead and add them in as I talk about them. The radius is the radius everywhere, right? That's a circle, so I'm going to put an R there. These y values, they are the same, right? They go up to the same heights. They go up to the same height. They appear to anyway. The x's have the same value as well, except for the fact that this x is to the right and this x is going to be to the left. So that would be a negative x value. Now the y values are both positive. They both go in an upward direction, but the x's are technically in opposite directions. All right, so now let's suppose that we're going to evaluate the sine and the cosine of both of these angles. If we were to evaluate the sine and the cosine of both of the angles, remember that the pictures of these two angles look pretty much the same except for the differences that x value here. Okay, so I have a couple of statements that I want to use to guide us through what we should see when we evaluate these. The first says that the sine of 40 and the sine of 140 have the same blank value, so by definition, we can complete this statement here. They have the same blank value by definition. Okay, so let's go back to the definition part. The definition of sine, so sine theta is equal to the y value divided by the r value. And in the picture, both of these angles, 40 degrees and 140 degrees, they actually have the exact same y value. So of course they have the same radius. If they also have the same y value, how should they differ when we evaluate them? Those are the only things that are used to evaluate them. Okay, so they have the same y value. They have the same y value. Of course, they also have the same radius. So let's evaluate these in the calculator and see what that says. Let's take the sine of 40. Okay, and we get that number that we might not really recognize what it is, but we get that number when we evaluate the sine of 40. If we evaluate the sine of 140, we get the exact same answer. And that should make sense. They have, in the picture, they have the same y value, and they have the same radius. They have to evaluate as the same thing. Okay, so we can complete this statement here that the sine of 40 degrees is the exact same thing as the sine of 140 degrees. All right, now let's take a look at cosine. The cosine of 40 degrees and the cosine of 140 have opposite blank values. Okay, let's think again, definition for cosine. The definition of cosine theta is equal to x over r. We have the same argument for r, that all the r's are the same in the picture. But they're x's. Being that the first angle, 40 degrees in quadrant 1, you have a positive x value. But the other angle, 140 degrees, being in quadrant 2, has a negative x value. Okay, so in a way they have the same x value, except that they were actually opposites, one positive, one negative. They have opposite x values. So by definition, how would they compare? So in the fraction, they have the same denominator. It's just that the numerator, it's either going to be a positive x value or a negative x value. So when we evaluate in the calculator, we should see that we get the same value except a different sign to go with it. So let's check that out. We'll take the cosine of 40. That gives us that number, 0.766 and some more. Type in cosine of 140, and you get the same value, except that that one is negative. It's negative because we're in quadrant 2. All right, so a statement that we could write is that the cosine of 40 degrees is equal to the opposite of the cosine of 140 degrees. And what that means is that if you were to evaluate cosine 140, get that answer, then negate it, switch its sign, it becomes the answer that we have for cosine 40. Every angle can be related to a reference angle. The reference angle is the shortest angle measured from the terminal ray to the x-axis. It is very important that you know that this will be related to the x-axis. Okay, make sure we make a mental note of that right now. Okay, so every angle has a reference angle. The reference angle is the shortest angle measured from the terminal ray to the x-axis. The sine or cosine of every angle with the same reference angle measure have the same absolute value. Whether it's positive or negative will depend on the quadrant that we're looking at. For example number 1, what we're going to do is take a look at a couple of angle measurements that are well beyond the first quadrant, 238 degrees, and then we've got 5 pi over 3, which is in radians. Okay, and now that is also well beyond the first quadrant. I believe that one is in the 4th quadrant there. Okay, we're going to evaluate these, and we're going to start by evaluating them in a calculator just to have a value for it. Once we have that, we're going to look at what the reference angle is, and then we're going to evaluate for the reference angle and see how that answer compares to the answer that we originally get. All right, so the sine of 238 is going to give us this number here. Let's go ahead and just jot that down. It is negative 0.848. Okay, we're going to round that off just 3 places there. Okay, so that's a value we get, and we don't really know much about what that is. But once we start to draw a picture of it, some of the things about it are going to start to make sense. Okay, so here's a coordinate system. We got quadrant 1, 2, 3, and 4. In degrees, this would be 0 degrees. This would be 90 degrees. That'd be 180. This would be 270, and then of course it's back to 360. And 238 is gonna sit somewhere around here. It's gonna be in this area, okay? Now I'm gonna attempt to draw it a little bit closer to where it should be, okay? And the way that I'm gonna figure that out is I'm gonna compare the 238 to the 180 degrees. Now remember that above here, the reference angle, which is what we're about to create, the reference angle is the shortest angle measure from the terminal ray to the x-axis. Wherever I draw the 238, that is the terminal ray. The initial ray would be over here at the positive x-axis. Okay, so we rotate out to 238. Okay, and I want to look at the space between the x-axis and that terminal ray. Okay, so what I'm going to do is take 238, which is how far I'm going to rotate out, just go ahead and subtract 180, and it tells me that I'm offset by 58 degrees. Now, directly in between these two axes would be at a 45-degree angle, so we need 58, which case I'll just make it a little bit more in this direction over here. But we figured out through that whole process that the angle here is 58 degrees. And that's what we call a reference angle. So the argument is that every angle that we have can be related to a reference angle. 238 can be related to a reference angle of 58. And that 238 should evaluate the same as 58 degrees plus or minus the sine. So let's check that out. If I take the sine of 58, that'd be the sine of the reference angle, I get that number. Okay, the sine of 58 is equal to 0.848. Okay, so pretty much the same thing, except that that is negative. The real answer is actually going to be a negative answer. It's really going to be a negative. Now, why is that negative? Because sine is based off of y values. And if you're in quadrants 1 or 2, you have y values that are positives that are up here. But if you're in quadrants 3 or 4, you'd be negative. So if you can just remember that for sine functions, you're positive in the top, negative in the bottom, you can just take reference angles, figure out how far they are from 180 or how far they are from either 0 or 360, evaluate those numbers, and then just apply the right sign for what you have. So maybe we can summarize it this way. If we can figure out every angle that ranges from 0 to 90 degrees, we can then just transfer that information to the other 3 quadrants with that caution that you need to know where you're positive or negative. All right, let's go ahead and do a question that's in radians. The cosine of 5 pi over 3. We'll go ahead and just evaluate that, just so that we have that number out of the way. All right, the cosine, I'm currently set for degrees, which means I need to change that to radians. Go to the mode, just switch that up. All right, in radians, the cosine of 5 pi divided by 3 is going to give us 0.5. So that's a pretty convenient number right there for you. That one is going to be 0.5, same thing as 1/2. All right, now let's go ahead and draw a picture. Let's figure out where that angle actually is. Once we have that, we can talk about a reference angle that goes with it. We're in radians. We have 0 radians. Over here will be pi radians, or 3.14 approximately, but best if we can do it in terms of pi. Plus our question starts in terms of pi, so we'd use that. Over here, this would also be 2 pi, okay? Out of fractions, just either 0 or it's 2 pi. 5 pi over 3. All right, remember that the top is pi, that this is pi, and then you got another pi down there. So we've got 5/3 of a pi. Okay, 3/3 of a pi would actually get you to pi. So you want to look at that denominator and think about using that to divide up one of the sides here by that amount. I don't know how exact I can do that. well, 180 degrees is going to be at 60, so I can probably just borrow that idea. So it'd be here, and it'd be here. Okay, try and make this look right. I'll do little dashes here. Okay, so that would be pi over 3. That would be a third of a pi. And then over here, that would be another third of a pi, and then you got one more third of a pi. Okay, so 3/3 pi. But we need to get to 5/3 pi. Okay, so you can actually just extend that out. That would be 4. And then out to here, that would be 5. So 1/3, 2/3, 3/3, 4/3, 5/3. This is 5/3 pi, or 5 pi over 3. All right, now, reference angle though. The reference angle is always going to be the shortest distance, the shortest angle measure to the x-axis, Okay, so in the other one, what we did is we measured back. We had to go that direction to get to the x-axis. In this picture, we have to measure forward. We have to continue on to get to that x-axis. And that space, just like it is up here, would be pi over 3. So your reference angle to 5 pi over 3 is pi over 3. So we're going to evaluate that, the cosine of pi over 3. And oops, got to divide it. All right, the cosine of pi over 3 is also 0.5. It's exactly the same answer. It is 0.5, not opposites in this case. Now, why is that? For cosine, here you are positive on the right because that would be where you have positive x values, and then you're negative on the left. Okay, so if you end up in quadrant 4, the answer that you get by using the reference angle is still going to be the same answer to what you would have gotten with your original angle. For example number 2, we're going to go back to looking at our special angle measurements. We actually have 5 special angle measurements. Previously, we had really focused our attention on just 3 of them, which was the 30, 45, and the 60, because when we had looked at that information, it was about right triangle trigonometry, and we were really thinking of the acute angle measurements that we had there. So those made sense. The others we couldn't actually use for the thetas in those pictures. All right, now as a heads up, these angle measurements, these 5 that you're going to see here, are going to be the most important ones that you know moving forward. You will have these memorized at some point. You will know these. Okay, now let me go back to example 1 real quick. 58 degrees, that is not an angle that you're going to memorize the answer to. You're not going to know off just the top of your head what the sine of 58 would be. However, over here, our reference angle is pi over 3. That is something that you're going to have memorized. You're going to know that one because pi over 3 is actually just 60 degrees. Right? If you divide 180 by 3, and pi being 180, if you divide 180 by 3, you get 60 degrees. So we're really going to do 2 things here. We're now going to bring in the radian measures that you want to associate with these degree measurements, and we're going to create a list of all the values that we would expect by evaluating either the sine or the cosine of each of these. All right, let's go ahead and get the radian column filled in first. All right, so 60 degrees is going to be pi over 3, because if you divided 180 by 3, you get 60. Okay, pi is 180 degrees. All right, what would you have to divide 180 by to get 45? You'd have to divide by 4. So this is pi over 4. What would you have to divide 180 by to get 30? That's 6. What would you have to divide 180 by to get 90? That would be 2, so this would be pi over 2. So those are your radian measurements. You are going to want to memorize these values together. Of course, you could always use the method that I just described there by thinking about division to reproduce these if you need, but it is best if you just memorize them. All right, next, what are all of these, whether they're degrees or they're radians, what are they when they go into the sine and the cosine? Now, to save a little bit of time here, this middle section, we already did that stuff, okay? So I'm not going to prove why these answers are what they are. They are proven previously. All right, so the sine of 30 degrees was 1/2. The cosine of 30 degrees was square root 3/2. The sine and cosine of 45 degrees was square root 2/2. Those ended up being the same. And we actually just did that one, okay? We just did that one, at least for cosine. The cosine of 60 or the cosine of pi/3 turned out to be 1/2. That one turned out to be 1/2. But if you were to do that with sine, take the sine of either of those two, you would get the square root of 3/2. You would get those values. So here's an observation that I think is really neat. If you look at the values here, we've got 1/2 here. We've got the same value there. Then we got the square root 3/2 there. That they just seem to alternate in their direction. Okay, and one of the reasons that that's true is that these are complements to each other. Now, we haven't really talked about that yet, but it will appear at some point. The 30 and the 60 degrees are complements. So the 30 of sine, or the sine of 30, is going to be the same thing as the cosine of 60. Likewise, the cosine of 30 will be the same thing as the sine of 60 because these are complements to each other. And in fact, 45 degrees is the complement of itself, so that would explain why these two are the same. All right, now the 4 that we haven't figured out yet officially that we want to put in the table here would be at 0 degrees and 90 degrees. Things that you can't quite do. Things that you can't quite do with a right triangle. But if we take a look at these circles, that would be sine, and just talk about the what we have for the quadrants, go back to the definitions of the y value of the r. We're going to do all that. I'm going to use the pictures as an aid here. All right, the sine of 0. The sine of 0 is looking at right here. You're going to notice that that sits right between a positive and a negative. It's going to sit right between a positive and negative. The transitional value between positive and negative is 0. Now we can also confirm it based on the definition. Sine is going to be the y value divided by the radius. And right here, you don't have any y value. You're strictly an x value that takes you out. There's no y value, so you have 0 divided by the radius, which is 0. All right, let's go ahead and look down here at the sine of 90. At this spot, you're between two positives, so you'll get a positive answer. But at that location, you don't have any x value. There's no x component. You are 100% the y value. Your y value is directly up all the way to the top of the circle, which means that the y value is the same thing as the radius. Okay, and if you had a fraction, y over r, and these values are the same, it reduces down to 1 whole. For cosine, cosine is 0 is right here, directly between the two positives in this case, directly between two positive, which is what we saw here with the sine, directly between two positives, that is completely x value, no y value, so your x is the same thing as the radius, that would reduce down to 1. And if we look at the cosine of 90 degrees, which would be up here, you're right between the positive and the negative. You have absolutely no x value, which means you'd be doing 0 divided by r, so that is 0. And then you see in the table that the flow of values, that direction for sine, is in the opposite direction for cosine. You even get at the ends here. What's the complement to 0? 90 degrees. So the sine of 0 is the same thing as the cosine of 90. And the cosine of 0 would be the same thing as the sine of 90.
Later, blah.